Thank you everyone. We start again to the channel Bidyut flow. We also demand you to subscribe this channel as soon as possible because the channel is running faster than faster. We start today the residual part, which is the final part of the first lesson, electric field and potential of class 12. The problem says to us, two large metal plates, A and B, are placed parallel to each other in free space. Their surface charge densities are sigma 1 and sigma 2 respectively, where sigma 1 greater than sigma 2, and the distance between them is d. So let us go to our task first. Suppose these two large metal plates A and B, which are parallel to each other. This is for sigma 1, this is for sigma 2, and the distance between them equals to d. A point charge Q covers the distance of A, which is less than d, from A to B at an angle of pi by 4. So from A to B at an angle of pi by 4. This is the pi by 4 angle, covers the distance A to B, and this is A, covers a distance of A, less than D, from A to B. Covers a distance of A less than D. From A to B, resultant field intensity. So this is A. So this is A. This is A. So what is this? This is A dash. Because there is a sigma 1 and sigma 2 surface charge densities. So the field intensity nearer to the plate 1 equals to sigma 1 upon twice epsilon 0. Sigma 1 upon twice epsilon 0, which comes from Gauss theorem. Sigma 1 by twice epsilon naught. And for this plate, this will be sigma 2 by twice epsilon naught. But in between these two plates, suppose here is a point. This point faces two opposite forces, because if this is positively charged and this is also positively charged, then if a unit positive charge placed here, so this will repel it and this will also repel it. So there is an opposite force at that point P. If this is negative charge, if this is also negatively charged, then also there is a opposite force, such like the statement said. So we can write the effective electric field as sigma 1 minus sigma 2 divided by twice epsilon 0. Effective E net equals to this. So answer A is the correct one. Answer A is the correct one. Again I am saying, from Gauss theorem we get the field intensity nearest to the plate 1, this large metal plate, and this is also large metal plate, so equals to sigma upon twice epsilon naught. How sigma upon twice epsilon naught? It is beyond our limitation, because the question is of 1 mark. It will take some other into other question, which I will show you in the later part. So answer A is the right one. And number 2, resultant field intensity B is cross, so this is the right one. Work done. Now work done. What is the work done? Work done equals to effective E into Q into A dash. Effective E into Q. This is force, because you know electric field into the charge carried equals to force, and here is this force applied for A dash distance. So we can write this equals to sigma 1 minus sigma 2 this divided twice epsilon naught into Q into A dash equal to A cos pi by 4 equals to cos pi by 1 by root 2. So sigma 1 minus sigma 2 this divided by twice epsilon 0 into Q A. So answer also C is the correct one. So answer A and answer C are the correct one. Another typical problem. A dipole is placed in XY plane. Suppose the floor is XY plane parallel to the line Y equals to twice X. So suppose this is the XY plane. The plane of the board is XY plane. So this is X axis, this is Y axis. Suppose this is the XY plane. So Y equals to twice X. This is the Y equals to twice X. A straight line passing through the origin, because we know Y equal to mx plus c is the straight line, is equation of straight line passing not through the origin, and when it passes through origin, so Y equal to mx. So here m equals to 2. The problem says that a dipole is lying in this xy plane. A dipole is lying in this xy plane. Net force acting on the dipole is 0. Net force, because in this direction there is electric field, so there also electric field along z-axis. This is z-axis. So along this direction, electric field is present. So we know tau equals to P cross E. Tau is the torque acting on the dipole, and P is the dipole moment of that dipole which is situated in the xy plane. So P cross E is the tau, because this says that the torque acting on net force acting on the dipole is 0, but it can experience some torque. So this is E and this is P on the xy plane. So P cross E, when you take P in xy board, P cross E, you get torque along the xy plane. First we have to take the concept clear. When P in xy plane, and when P cross E, you get that vector is also perpendicular to P, and that is also perpendicular to E, which only possible when the torque lies in the xy plane. When the torque lies in the xy plane, at plane xy, suppose there is a P, so this will be perpendicular to P, and this also will be perpendicular to E. So we decide as tau lies in the xy plane, and in the xy plane y and which is net force acting on the dipole is 0. It is not for granted here, but it can experience a torque. So we can show that it drives a torque. So y equal to twice x, which is the parallel to y equal to twice x. Parallel to y equals to rho. The dipole is present in this way, parallel to y axis. So perpendicular parallel to y axis. So perpendicular to this we have the gradient as m dash equals to minus half, because m dash equal to minus 1. So the equation of the line at which the torque is present can be given by these two, C and D, because here m dash equal to minus half, so equation of the straight line can be y equals to minus half x plus 0, or y equals to minus half x plus 2. This one is passing through origin, and this one is not passing through origin. So answer C and D. Again, a typical problem is taken into our board. In a certain region, positive charge is distributed so that the charge density equals to rho equals to kr, where r is the distance from the origin. the total flux linked with a spherical closed surface. So from Gauss theorem, we can write this one is the origin. Suppose this one is a Gaussian surface. This one is Gaussian surface. Which one is spherical? And suppose this one, it is the radius smaller. Suppose this is also a Gaussian surface, which is of r plus dr. So this cell, so this spherical cell is of volume because V equals to 4 pi r square dr. Because this is a 4/3 pi r cube, it can be simplified as V2 minus V1 equals to 4/3 pi r plus dr whole cube minus 4/3 pi r cube equals to 4/3 pi a cube plus 3a square b plus 3a b square plus b cube minus r cube equals to, because dr square and dr cube terms are neglected because dr is very small. So dr square and dr cube terms are neglected, and which is usually is neglected in the subject physics. So we can write V as equals to 4/3 pi into 3 r square dr, which is equal to 4 pi r square dr. So we can write Q as dq as 4 pi r square into rho into dr. So total charge Q equals to integral r equals to from 0 to r equals to capital R 4 pi r square kr dr, because rho equals to kr given. So we can write 4 pi k r cube dr equals to 4 pi k r to the so this is equals to pi k r to the power 4 pi k r to the power 4. Now total flux linked equals to q upon epsilon naught. So that is equal to pi k r to the power r to 4 upon epsilon naught. So the answer pi k r to the 4 upon epsilon, the answer B. Number 4, probably a typical problem also, here also, very easy also, but typical one. A block of mass m, this one is a block of mass m with a charge minus q, is placed on a smooth horizontal surface. The block is attached to a massless spring of force constant K fixed on a wall. Spring is fixed on a wall. If a uniform electric field is applied, then what will be the amount of compression in the spring? First, take the concept clear. There is a block of mass m with a charge minus q. There is the electric field E directed along this direction. So, we can write that y is directed in this direction because there is some positive charge present inside this field, so that if a unit positive charge placed here, the force of repulsion gives the direction, which one is shown here. So here is a minus q charge, so this one will be attracted by this one positive charge if placed in the other ground of this electric field. So there is a force of attraction, but the spring also will be contracted due to this force. So what will be the amount of compression? Suppose x is the amount of compression. So we can write this force F into x equals to the, when the spring will be contracted, then it will get some potential energy, and that potential energy equals to half kx square. From we get EQ x equal to half kx square. From this we get x is cutting out, x equals to twice EQ upon k. So answer B. This is a graphical problem which is of a problem of a charged spherical conductor, and the center of the spherical conductor is taken as origin, and the radius of the spherical conductor is taken into the small r axis, which is starting from origin of the sphere. Mind it, when the small r equals to capital R, then the sphere completed, and the smaller axis is not ending. Smaller axis also running outside the spherical conductor. We have to find the correct one, because C is the correct one. Why? Now we know inside a spherical charged conductor, electric field is zero. and outside the conductor equals to q by 4 pi epsilon naught r square. Because this one is obtained by Gauss concept. How? 4 pi, taking a spherical surface, we get 4 pi r square equals to q upon epsilon naught. Total electric flux equal to 1 by epsilon 0 times the charge present inside the hypothetical spherical surface. Here electric field obtained, electric field is obtained, so where there is electric field there is a charge. So surrounding this you can write E equals to this, but here E equals to E varies 1 by r square, which means the outside the conductor electric field is inversely proportional to the square of the distance. So this one is a graph which is for this characteristics. So say answer C is the correct one. This problem is the last problem for this class. The next class we start capacitance and capacitors. Here the problem says, let there be a spherical symmetric charge distribution with charge density varying as rho r equals to this. So we can write for r less than equal to r and rho r equals to 0 for r less than equal to capital R, where r is the distance from the origin. Electric field at a distance r less than r is from the origin. What is capital R? Capital R is the radius of the spherically sphere, radius of the sphere. So we can write here total. This one is a Gaussian surface, small r from O. This is the small r going this way. So if the spherical shell is considered of radius r and radius r plus dr, then we get total Q equals to 4 pi r square rho r dr r is 0 to capital R. Here is the electric field at a distance r from the origin. So here is a small r, not capital R. So this is equal to 4 pi r square rho 0 5 by 4 minus this dr 0 to this equals to 4 pi rho 0. Five by 4 minus this into r square dr equals to 4 pi rho 0. 5 by 4 r cube by 3 minus by r cube of 4 by 4. This. So now E into 4 pi r square equals to 4 pi rho 0 r cube by 5 rho 0 r cube 5 by 3 minus r by r. So equals to the printer is the printer where is it? Because Gauss theorem says so. So answer B. So the channel Bidyut flow runs faster, and please subscribe this channel so that the problems in this way will be solved day by day. Thank you.